Okay, really neat idea here. Unit circle picture, okay? And you got vectors number 2 through 12, okay? The number 2 vector, you know from what you know about the unit circle, has approximate coordinates 0.9, 0.5. You should know that very well at this point. And this would be 0.5, 0.9, and then you have positives and negatives, you have 1, 0, 0, 1, all that, right? Okay? So instead of 0.9 and 0.5, we're using 0.87 and 0.5 because 0.87 is a better approximation to the coordinates of this point. Okay? So that should be pretty obvious. And we have a set of vectors that we express as 1, 0, 0.87, 0.5, 0.5, 0.87, 0, 1. Okay? Now, either Will or I always has to close the door depending which one was talking louder this day. Okay. He closed his yesterday when I was saying something to you guys going out. So, okay, anyhow. So we understand that set of vectors as being these vectors from here to here. Okay? And now we've got a matrix. It's not a stochastic matrix, is it? Because columns don't add up to 1. Okay? And if you multiply it by a vector, the sum of the two numbers here is not going to be the sum of the numbers you get when you do the multiplication. Now you did prove, and most of you either proved or came close to proving in your homework, that for any stochastic matrix, the sum of the vectors doesn't change. Okay? If the sum of the columns is 1, the sum of the vectors doesn't change. Okay. So we define a function, t of w, and I call it t1 of w because here's your transformation t1. Okay? We're doing the transformation t1 to get these vectors. Okay, so t1 of w, it just the vector a times v, where v is a member of the set S. You know that symbol? Everybody should know that symbol. It just means is a member of the set. So what's the set? The set is these vectors. What are the members? This, 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 and this, right? So v is one of these vectors. Fair enough?
Yeah.
So we actually go ahead and do it. So, you know, it's just a times v, so the transformation takes vector 1, 0. Well, you just multiply 1, 0 by the matrix, and you get this vector here. Takes the vector 1, 0, which is number 1 here in purple, to the vector 0.8, 0.6. So it means that this vector, here goes Beethoven again, this vector here becomes 0.8, 0.6, which is here. Okay? Fair enough? Pretty simple. And then we multiply the same matrix by 0.87, 0.5, which is vector 2, and we get this, which is vector 2 here. So this thing transforms this vector to this one, this vector to this one, and so forth. We do this to all the vectors, and it's all right here, at least all the vectors in the first quadrant, okay? And we see that 1, 2, 3, and 4 go here. 1, 2, 3, and 4, right? So what would you say has happened to this picture? The matrix takes this picture and transforms it to this picture. How would you describe what happens? Yeah, it's all rotated, okay, through some angle. Now we could figure out the angle, but we're not that interested in this particular rotation. Although rotations are a big deal, stochastic matrices don't rotate things. Okay? At least they're not a pure rotation. Turns out any transformation can be expressed as a rotation and a set of stretches and stuff, but we're not going to have time to get into that. Okay, now we got a transformation 2 here, and it's not stochastic either. Okay? So here's the transformation. And to see what the transformation does, you just multiply the matrix by every one of these vectors and get a picture. Okay? So we multiply by the 1, 0 vector, this one, and we get 2, 0. Oh, there it is. Okay? And so forth. And the vectors do something like this. Okay? And what happens is, the 2 here basically stretches everything in this picture out by a factor of 2. So it's like you take a flexible sheet of rubber or something, write this on it, and stretch it out to twice its width, and then stretch it out to 3 times its length, because of the 3 here, and also flip it over this way. And that's the effect of this matrix. Okay? Now, what we want to look at is what happens to the directions of these vectors. And we want to maybe ask ourselves, is there any vector that maintains its original direction? Well, it's very clear that vectors 1 and 4 maintain their original directions, right? Okay? A vector that maintains its original direction is called an eigenvector, and each eigenvector has an eigenvalue. Okay? Eigen kind of means same, but not exactly the same. Okay? The vector has the same direction, but it's going to have a different length. Okay? So what happens to this vector with this transformation is it maintains its direction, but it doubles its length, as you can see here. 1, 0 has the same direction as 2, 0. It's in the direction of the x-axis. Okay? And it's expanded by a factor of 2. Okay? And this blue vector here is in the direction of the y-axis. Okay? Now, it turns out that vector 4 doesn't have exactly the same direction as the vector you get when you transform it, because this vector is the transformation of vector 10. Okay, so the vector gets 3 times as long, but reverses its direction. So this vector here is what you get from this vector here. It's along the same line, so it's still a multiple of itself, but it's in the opposite direction. Okay? Now, does that halfway make sense? That you can multiply these things, and if you think about this a little bit, you can see that this vector here goes to a vector here that's 3 times as long and in the opposite direction. Okay? Now, there's more to it, but an eigenvector satisfies this. The matrix A multiplied by the vector is a multiple of V itself. Okay? Now let's test that. Okay, for the first transformation here, which is pictured here, and you can do this picture, and I'll ask you to do this picture for a couple of transformations. Probably a stochastic transformation that you already know something about, like the original same-dimensional. And then we'll talk about it a little more tomorrow. Is there any vector 1 through 12 here that ends up on the same line here that it was here? Where does vector 1 go? It goes here. Well, vector 1's along this line, and the transform vector's along this line. It's not along the same line, right? Take another one, vector 6. Vector 6 is along this line. Vector 12 and 6 are along the same line. Okay? They're just equal and opposite. Even though, drawing didn't really show that. But vectors 6 and 12 here are along this line here, but they're along this line here. Well, you can think about it. Since every vector is rotated through some angle, okay, and it's easy to calculate that angle. We got to use a little trig, and we're not going to do that. None of them can be along the same line. Okay? So I can say this. Can't happen for the rotation matrix 0.8, negative 0.6, 0.6, 0.8. We see why? Because all the vectors get rotated. They can't be on the same line. Everything rotates around the origin. The whole wheel rotates. Nothing ends up on the same line. Okay?
Negative 0.6?
I'm sorry?
Is that negative 0.6?
No. Negative 0.6 here, 0.6 here. Again, you have to know a little more about trigonometry to show why that is. You know enough, I could explain it to you, but most people haven't had trigonometry yet, okay? Okay, so we're not going to do the trig of that, but you could easily figure it out. Okay. Now, does it happen here? Well, yeah, the purple vectors here are in the same direction as the purple vectors here, and the blue vectors are along the same line as the blue vectors, even though they reverse direction, right? Okay? So, for the 2, 0, 0, 3 matrix, what happens? I'm going to use this little arrow with a kind of a base thing here. 1, 0 goes to 2, 0. Which is along the same line. And don't have the picture anymore because I have a way of supporting the board over there. Need to have this one. Okay, so it's on the same line. And 0, 1 gets transformed to 0, negative 3. Right? And you can easily see that from the diagram. Okay? So we can say a little more. Okay, so I'm going to say it this way. One 0 transforms to 2 times 1, 0. Why would I say that?
Because it doubles.
Again?
Because it doubles?
Yeah, well, 1, 0 goes to 2, 0. It doubles, and that's a good way to look at it. But if you multiply 2 times 1, 0, you get 2, 0, right? Mm-hmm. Okay, now I haven't defined multiplication by constant, but it's intuitive and obvious, okay? So, x0 goes to 2 times x0. Does it make sense that that would be so? If I replace the 1 by x, it still works. Now it requires a little proof and some definitions, but it's pretty straightforward and it seems pretty obvious. Okay? If you double, if transformation doubles one number, it should double another number. If it doubles one vector, it'll double another vector. Okay? And also, 0, 1 goes to -3 times 0, 1. And in general, 0y transforms to -3 times 0y. Okay, now, big deal is this eigenvalue equation. So the eigenvalue here, so I'm going to say one, 0 is an eigenvector with eigenvalue 2. And zero, 1 is an eigenvector. And what's its eigenvalue?
-3.
Yeah. I mean, why do I say this has eigenvalue 2? It's because it gets doubled, right? And what happens to this one? It gets tripled and reversed, right? It gets tripled and flipped. So with eigenvalue -3. Now there's a lot that we can do with eigenvalues, including explain how the vectors in a sane-dimensional transformation approach a limit, approach the stable population. Okay? We're going to develop a little machinery to do that, and we'll give you some homework and just, mapping a thing and then observing some things about the mapping, okay? Develop a little machinery, and then I'll show you something that's really pretty darn neat, okay? And very profound in its implications and the insights you can get from it. Okay, so I'm going to make a jump here. So a vector x, y is an eigenvector for matrix A if A multiplied by xy equals lambda times xy. They probably don't know the Greek alphabet, but you might know some of it, alpha, beta, stuff like that. That's just another letter in the Greek alphabet, lambda. Okay? Not hard to make. So, lambda is the eigenvalue. So you have this equation. Well, let's see if the sane-dimensional matrix has eigenvalues and eigenvectors. our basic same-dimensional matrix, stochastic matrix. We want to solve A times xy equals lambda times xy. Now I'm going to move this board down here for a while so I can move the other board the way I'd like to. Okay. Okay, well, what is this? We can write this out. We can replace A by the matrix, right? Okay, so this says that 0.9, 0.2, 0.1, 0.8 multiplied by xy equals lambda times xy. Now, if we multiply this out, 0.9, 0.2 times xy tells us that 0.9x plus 0.2y, 0.1x plus 0.8y has to equal, and we can multiply this out, this is lambda x, lambda y. Now, how could this possibly be equal to this? What does it mean for two vectors to be equal? It means that the first element here, the first row has to equal the first row, right? Two vectors can't be the same if their first rows are different. Okay? And also the second row has to equal the second row. Okay? These are equal if and only if 9x, 0.9x plus 0.2y equals lambda x, and 0.1x plus 0.8y equals lambda y. Okay? Well, what's that? That's just a set of simultaneous equations, two simultaneous equations. Unfortunately, they're kind of three unknowns. Okay? But we can get around that. So, .9 minus lambda times x plus 0.2y equals 0. I'm just subtracting lambda x from both sides and factoring out the x, right? And 0.1x plus 0.8 minus lambda y also has to equal 0. So, y over x has to equal what? Well, move this over to this side, we get 0.2y equals a negative of this, right?
What?
Sorry?
I don't get it. I don't get it.
Well, you have to think about it. Okay? Yeah. Not going to stop. We'll bring this out in some homework problems, okay? Now, first of all, but let's make sure we understand the steps. What you don't get is where we're headed and what's going on, okay? First of all, do we understand why you have a 0.9 minus lambda here?
No.
What do you get if you subtract lambda x from both sides of this equation? You're going to get 0.9x minus lambda x, right? Your x's are going to be 0.9x minus lambda x. And then you factor the x out and you get 0.9 minus lambda times x. So if you don't see this step, that's something we can fill in easily. So just doing the scheme of it. You get from here to here in a very simple, easily understood way that we're not going to take time because of, you know, having to get a lot of stuff done by 10:30 that we can then clean up later, okay? So from here to here, it's very easy. Just accept that for right now, okay? Don't try to understand every step. When you get into college level math courses with a college level pace, you're going to be in the same situation. You're going to say, you know, what's this foolishness? Okay? How do we get from there to there? You can't stop and worry about it because nobody's going to stop and answer your question. Nobody's going to stop the lecture and triple the time required for the lecture to answer that question. They're going to expect you to take notes and look at the general scheme of it and then fill this in later. And it's going to be something that's hopefully very easy to fill in, but we don't have time to discuss it right now, okay? Now, we can talk about it. We can answer this a little bit later and even put it in the videos so that anybody has to leave in an hour and a half or an hour can also fill that in. But we're not going to stop now and fill it in, and nor will you stop and fill it in a demanding college level course, okay? If you go to engineering or some science at Virginia Tech, your professor's going to say, fill it in later, okay? And that's what I'm going to say right now. It doesn't mean we're not going to fill it in later. I'll take the time to do that. Okay, but anyhow, or I'll give you a homework problem that just says, okay, subtract lambda x from both sides and group your x's. Then factor out x. What do you get? Oh, yeah, now I see why it is, okay? And you can expect that in a rigorous college level math course too. I give you the overview here. I show you where it's going, or your professor does, and then the problems help you fill in the details, okay? And at the higher level courses, you get better at filling in the details. But don't get hung up at this point on this. You probably will start missing steps fairly early in a lecture. You look at the overview and don't worry about where that 0.78 came from. Just accept that you'll be able to figure that out when you review your notes. Okay? Okay, so y over x is from the first equation. And all I'm doing is I'm putting this over on the other side and dividing by 0.2. Okay? And from the second equation, y over x equals negative 0.1 over 0.8 minus lambda. And there's no step in any of this that is not pretty easy to understand. What in the world? I don't have that in there. Oh yeah, I know. Okay. Okay, so now I know that this equals this, right? Okay? And that's an equation you can easily solve. You just multiply both sides by 0.2 times 0.8 minus lambda, which is equivalent to this superstition of cross multiplication. Okay? And I'm not going to go through the details. You get 0.9 minus lambda times 0.8 minus lambda equals 0.02. Now what kind of an equation is that? Lambda is your variable. What kind of an equation do you have? Okay, now if you've had Algebra 2 or pre-calculus, you should have been drilled a little more in being able to recognize what kind of equation you have. You probably weren't, I'm sorry?
It's a quadratic.
Yeah, it's a quadratic equation. Not everybody will pick up on that. Not even a smart group like you who's had, you know, at least reasonably decent courses that, you know, because of SOL had to focus on some things, not others. Not all that important for the SOL to recognize what kind of equation you have. As long as you got the right superstition going, you can solve it. Yeah? No, both of these are negative, so I didn't write the negatives down. If this is equal to this, then if you take the negatives away, they're equal. Okay? And that's another little detail that you would probably figure out if you just did what follows from this, which is set this equal to this. You'd have the negatives in it, and then you'd say, well, I don't want those negatives. I'll multiply everything by -1. And then you'd have this, and then you'd see why I wrote it this way, right? So I'm skipping steps. And you can be guaranteed that in a rigorous course, trivial steps would get skipped. Trivial steps would get skipped. That's kind of a little tongue twister, isn't it? Trivial steps would get skipped. Trivial steps would get skipped. I did it, the T's and the A's. I don't know. Try saying it a dozen times in a row, see if you can do it. Okay, so anyhow, we have this. This is a quadratic equation. In the variable lambda question, you know. So now we can say that lambda squared minus 0.17 lambda plus 0.72 minus 0.2, so that'd be plus 0.7 equals 0. And it's not 0.17, it's 1.7. Okay? And lo and behold, this factors. Anybody see how it factors? Well, probably not instantly, so I'll just write it down and you'll believe me. You get lambda minus 1, times lambda minus 0.7 equals 0. You can verify that by multiplying it back.
Minus 0.7.
And if you can't do it, and usually, you know, if I write a little different matrix, you're probably going to get numbers that don't factor and you have to use a quadratic formula, but it's always going to work out. Okay? So, lambda's 1 or